All right, so we are going to be talking about power series in this series of videos, for lack of a better way to go about that. And so what makes a power series different is you actually have an X inside your series here. So some other series that we might have found in the past, like a geometric series, had 4 and then a number raised to the n, correct? Or maybe like n over 3 to the n. So there weren't x values necessarily in place here. And power series, there are. So if we have this, we call it centered at 0, then notice that you're going to end up getting a polynomial in your expansion here rather than just a number. If you have a power series that's not centered at 0, it's centered at some other x value a, think about your transformations of parent functions, and that like x minus a means move this power series to the right a, so that you're centered now at a. But what makes this a power series is that you have x to a power inside your series formula. So let's first just talk about center and kind of how power series are going to work. So looking here at a, I have a series of n factorial and then x to the n. Well, since I don't have x plus or minus any number, I'm going to say that the center must be at 0. And then let's write out the first 5 terms. Now notice on this one, I'm starting at n equals 0. So my first term is going to be 0 factorial x to the 0. My next term is going to be 1 factorial x to the 1. The next term is going to be 2 factorial x to the 2. And then my next term is going to be 3 factorial x to the 3rd. 0 factorial, just as a property, is 1. X to the 0 is 1, so I get 1 plus 1x plus 2x squared. Now 3 factorial, 3 times 2 times 1, 6x cubed, and then we would go so on and so forth. All right, let's look at another one. So in this case, I have x plus 1. Now remember, our series is centered at a when we have x minus a. So this must be centered at -1. If I have a positive on the inside, remember that means move everything to the left. So my center must now be at -1. So let's go ahead again. We're starting at 0. So it's going to be x minus 1 to the 0 over 0 factorial plus x plus 1 to the 1 over 1 factorial, x plus 1 squared over 2 factorial, x plus 3, x plus 1, 1 is my center, 3 goes here over 3 factorial. And I'm not going to simplify that, I just want to make sure that we see this pattern here, that we're generating polynomials with this power series, not just numbers. All right, let's look at our last one. Here I have x minus 3. That means that a must be 3 or my centered at 3. This one I start at 1. Well, that's because I can't start at 0 because n's in the denominator. So my very first term actually must be x minus 3 to the 1 over 1. X minus 3 squared over 2. X minus 3 cubed over 3. X minus 3 to the 4th over 4. And so notice that my terms are a little bit different here because I'm starting at n equals 1. I can't start at n equals 0. I would have an undefined series or like term of that series, so I couldn't start there. So I'm going to have to start that one at 1 and how that kind of affects the first terms in the sequence. All right, so let's look at geometric series again, where we have r to the n. Now remember our geometric series, when we learned this, we said n had to go to 1 to infinity, and a was times r to the n minus 1. Now if I fix this a little bit, notice if I let n equal to 0, it kind of moves things back, so that way I have x to the 0 first. But if I plug in 1 here, I end up getting r to the 0 anyway. So that's why it starts at a and then ar okay? I could start this at 0 and then just adjust what my A value is, and that's possible to do that as well, okay? Now remember, this only converges if the absolute value of that radius is less than or equal to 1, and the sum of that series ends up being A over 1 minus R. Therefore, it must be true for this series that as long as x as the absolute value is less than 1, then this must converge to A equals 1, R equals x. So this series, 1 plus x squared, this infinite polynomial, if you keep adding on degrees, so like x to the infinite degree, it ends up equaling 1 over x as long as we are in this domain bound. Now let's kind of go back at the very beginning of college algebra, and then we never talk about it again. Let's talk about absolute value inequalities. If the absolute value has to be less than 1, absolute value of x has to be less than 1, then that means numbers like between 0 and 1, but then also there are negatives, right? So this means that x is bounded on the bottom by -1, then on the top by 1. And so think about like, yes, -1/2, absolute value less than 1, that works. Okay, more on this interval in a little bit, but let's go ahead and pull up a graph, and I want to show you why this works. So here I am in Desmos. I'm going to put in our sum equation, and I'm going to say that that's then equal to y equals 1. Well, only at 0, 1, right? Is that the case? But let's look at 1 plus x. Oh, well, that would be the tangent line to the curve at 1. And I bet if we zoom in really, really far, we could say like, okay, yeah, like that line and the function converge. They are about the same for an itty bitty domain of x, right? Well, what about if I then add x squared? And think of these as like when we're talking about partial sums, right? Oh goodness, look, it almost looks like I only have one function until I zoom out a little bit. And I'll zoom, right? So that's better approximation. Let's go up to x cubed. Even better, let's go up to x to the 4th. Even better. And so as long as I'm on this interval from -1 to 1, this infinite series, I'm just going to go out. Let's go out to x to the 10th. Okay, it's going to be convergent only though from x equals -1 to 1. So anything outside of that, I'm not going to be able to get a polynomial that models that rational function, okay, centered at 0. But I can get pretty close, and I can get something between -1 and 1 that does. That's the magic of power series. Let's go back to our notes. Okay, so we are able to represent this function then as the sum of that polynomials, and I want to just write it like this. I want to say, therefore, 1 over 1 minus x is actually equal to the series n equals 0 to infinity of x to the n. Like those are actually the same function, okay? That polynomial and that rational function are the same as long as you are between -1 and 1 for x, and you let that be an infinite polynomial. We saw with the partial sums, it wasn't quite exact, but an infinite polynomial, it will be from -1 to 1. Now, how do we write power series for functions? Notice that this function is f of x equals 1 over 1 minus -x cubed. That took a little mathemagic to unwrite that, okay? And I know that 1 over 1 minus x is this series. Oh, that was silly. N equals 0 to infinity. Well, think about if I'm then plugging in instead, I'm plugging in 4x negative x cubed. And so in place of x here, I could write this as the series negative x cubed to the n. And that's why function notation, y'all, has actually been really, really big deal for this whole time, is so that you can start seeing how these plug and play into our power series functions and how these are all kind of related. If we looked at this function, okay, and then if we took out the first couple terms of this, we would end up seeing that they are the same, again, on that interval, okay? And we'll talk more about interval of convergence in just a little bit, but because it's negative x cubed, negative 1 to 1 would actually still work here.